Now we are going to discuss about what is boundary layer thickness. Boundary layer thickness, it is defined as the distance from the boundary of the solid body measured in y direction, where the velocity, fluid velocity is equal to free stream velocity, where the fluid velocity is equal to 0.99 times the free stream velocity, that is known as boundary layer thickness, right. This is boundary. Boundary layer thickness is the distance measured from the boundary in the direction, in the y direction, at a point where the fluid velocity is approximately equal to free stream velocity. Free stream velocity is denoted by u, that is equal to 0.99 times the free stream velocity. Then this total thickness is nothing but boundary layer thickness. The boundary layer thickness is mentioned in three ways, that is, one, laminar thickness of the laminar boundary layer, that is denoted by delta n. Thickness of the turbulent boundary layer, that is denoted by delta tur, and thickness of the laminar sublayer, that is denoted by delta, right. This is about boundary layer thickness. Distance measured perpendicular to the boundary, by which the boundary layer should be displaced. This is the boundary layer. This is the boundary layer. That boundary layer should be displaced to an account of reduction in the flow rate, an account of boundary layer formation, Now we are going to derive the equation. What is the displacement thickness? Consider a liquid flows over the body at the free stream velocity is u, right. Now at a distance x, this is the leading edge, at a distance x from the leading edge, we are going to take one section, that is section 1,1. Okay, at this section we are going to take some dimensions that are, and also one more point, the velocity at point B, is 0, and the velocity at point C is equal to u, that is the free stream velocity. The velocity changes from 0 to free stream velocity u, right. Therefore, the velocity at the boundary or at a point B is equal to 0, and the velocity at point C is equal to free stream velocity, right. This is about this diagram. Now we are going to take one small elementary strip. The thickness of the elementary strip is equal to dy, that is y distance from the boundary, small u is the velocity of the flow over the elementary strip, right. Y is the distance of the elementary strip, dy is the thickness of the elementary strip, u is the velocity of the fluid at the elementary strip, and small b is the width of the elementary strip, right. Now we are going to derive the equation, the displacement thickness, right. Now we are going to take one small strip. This is the small strip. The thickness of the strip is equal to dy, and the width of the strip is equal to b, small b, and this is y distance from the boundary. The velocity over the strip is equal to small u, right. Now the area of the strip is equal to thickness is dy into width b. dy into b is the area of the strip. Now we are going to determine what is the mass of fluid flowing through the strip. Mass of fluid flowing through the strip per second is equal to, mass of fluid means mass density into volume, or mass density into discharge or velocity into area. Right, mass of fluid is equal to mass density of the fluid rho into velocity into area, or mass density into discharge q. Now this is the mass density rho into what is the velocity over the strip, that is small u, into what is the area, dy into b is the area. This is the mass of fluid flowing in the strip, that is dy. And next one, suppose if there is no any body, any solid body in the free stream velocity, for example, the water is flowing through the stream, if there is no any obstruction, that will maintain that same velocity. But here we have provided one boundary, because of that one solid body here, because of that here we are having the boundary layer. If there is no any boundary here, automatically the velocity flowing through this strip is free stream velocity. There is no boundary here, there is no boundary formation here. At that case, the velocity through the strip is equal to free stream velocity, that is capital U. Therefore, mass of fluid per second through the strip, absence of the boundary equal to, this is also same formula, mass density into velocity into area. What is the mass density? Mass density is denoted by rho into what is the area, what is the velocity through the strip. Velocity through the strip is equal to free stream velocity, that is free stream velocity is denoted by capital U, right, into what is the area, strip area is equal to dy is the depth into b is the width. This is the mass of fluid flowing through the strip if the absence of the plate. Now here the velocity absence of the plate is more than the velocity presence of the plate. Therefore, a reduction of mass that is equal to reduction of mass of the fluid through the strip is equal to, this is the mass of fluid, absence of the obstruction or solid body, mass of fluid, presence of the obstruction. Therefore, the difference between these two, this is say equation number 1, this is say equation number 2. The equation number 2 minus equation number 1, we are having the reduction of the mass of fluid, that is equal to rho into capital U into dy into b minus rho into small u into dy into b, right. Then now rho b into capital U minus small u into dy, right. This is the reduction of mass of fluid in this system. Okay. Now this is the loss of a reduction of mass, that is only through this strip. Now we are going to taking the reduction of mass per second for entire distance, that is from B to C. Reduction from entire strip, that is equal to mass reduction, total mass reduction for the entire strip BC, entire thickness BC is equal to integral 0 to delta P B capital U minus small u into dy. Here one new term, that is the delta. Delta is the thickness of the boundary layer, that is B to C. This is nothing but delta. Delta is the boundary layer thickness, that is B to C. Therefore, the total reduction mass equal to 0 to delta, integral 0 to delta rho B capital U, that is the free stream velocity, minus small u is the velocity at the strip into dy, right. Now this plate is displaced or shifted at a distance of delta star, and the velocity at a point delta star is capital U. The velocity at a delta star is capital U. Now mass of fluid through this entire delta star distance, mass of fluid through this entire delta star strip is equal to, here also mass density into velocity into area. Mass density is rho into what is the velocity in case of the plate is displaced at a distance delta star, the velocity at the zone equal to capital U. Therefore, the velocity equal to free stream velocity into area. What is the area? Delta star is the distance into B is the width. This is the area, right. If this is the mass of fluid, if the plate is displaced at a distance of delta star, right. Now, and also this is the mass of fluid, loss of mass of fluid. This loss of mass of fluid because of the compensation of the reduction in the mass of fluid, so that this is loss of mass of fluid per second, delta star is equal to this one. So this is the equation number 3. Now already we have derived total loss of mass per second through the entire BC, and this is the loss of mass through the delta star. Both losses, these equation number 3 and equation number 2 are equaling here, then we have the delta star, right. This is equal to equation number 3. Equation number 3 equal to rho into capital U into delta star into B is equal to, that is integral 0 to delta into P into B, right, into capital U minus small u into dy. This is equation number, already we have derived, this is this equation, equating these two, finally we have the delta star. Delta star is the displacement thickness. Now density cancel, width cancel, right. We have delta star u into delta star is equal to integral 0 to delta capital U minus small u into dy. Then delta star is equal to, one integral 0 to delta 1 by u bracket begin capital U minus small u dy, right. This is equal to, therefore delta star is equal to integral 0 to delta capital U by small u minus small u by capital U dy. This gets cancelled. Therefore delta star, that is the displacement thickness, is equal to integral 0 to delta 1 minus small u divided by capital U dy. This is the thickness of the displacement thickness. Displacement thickness delta star is equal to 0 to delta 1 minus small u divided by capital U bracket close into dy. Small u is the velocity over the strip. Capital U is the free stream velocity, right. This is about displacement thickness.
Last class we discussed about displacement thickness, laminar boundary layer, turbulent boundary layer and laminar sublayer. Now we are going to once repeat what we have discussed in the last class. Boundary layer, this is one solid body. If the water or fluid flowing over this solid body, so because of this fluid and this is the solid body, there is a contact between these two, fluid and solid body, because fluid having viscosity. Viscosity means that is nothing but liquid friction. Okay, viscosity is the property which offers resistance to movement of flow. So that because of the viscosity, there is a contact between the fluid and solid body. Because of that viscosity, the velocity over the solid body is 0. But the velocity of the flowing fluid is capital U, or the free stream velocity is capital U, even though the velocity over the solid body is 0. But away from the solid body, this is away from the solid body, the velocity of the flow gradually increases. Gradually increases. It means that the velocity of flow over the solid body is 0. Away from the solid body, the velocity of flow gradually increases. So that here we are having a velocity gradient. Velocity gradient. That means the velocity increases with respect to depth. With respect to depth. If the velocity is 0 at this boundary, shear stress tau is equal to mu into du by dy. If the velocity is 0, shear stress is equal to 0, because du by dy, velocity gradient is 0, therefore shear stress is equal to 0. The shear stress over the boundary is equal to 0 because velocity is 0. If the velocity gradually increases from boundary towards the y direction, automatically velocity gradient exists, so shear stress is also exists. Du by dy exists. But that velocity gradient is moving up to certain distance at some location, the velocity reaches to free stream velocity. Right? The velocity variation, the velocity at the boundary is 0, at the velocity at B is 0, at C is reaches to free stream velocity. Or the velocity varies from 0 to free stream velocity within a small distance from the boundary or within a narrow space. This narrow space is known as boundary layer. Be clear? The velocity varies from 0 to free stream velocity, that varies within the small zone or narrow zone. This narrow zone is known as a boundary layer. The theory discussed related to the boundary layer is known as boundary layer thickness. Right? This boundary layer thickness, this is nothing but boundary layer thickness. This boundary layer thickness is classified into two ways. One is within the boundary layer. This is within the boundary layer, beyond the boundary layer. Right? What is the difference? Within the boundary layer, what is the flow conditions? Beyond the boundary layer, what are the flow conditions? Right, within the boundary layer, the velocity varies from 0 to u or free stream velocity and also exists du by dy. Therefore, within the boundary layer, there is a chance to formation or there is a way to velocity gradient and also shear stress. Because that within the boundary layer, the velocity also gradually increases with respect to depth. Therefore, velocity gradient exists, so automatically shear stress is also exists within the boundary layer. Beyond the boundary layer, the velocity, same velocity maintained, constant stream velocity is maintained. Once touches this layer, once reaches to the free stream velocity, above the free stream velocity, the velocity is maintained, same velocity or constant velocity or free stream velocity. Therefore, there is no change in the velocity. Therefore, du by dy is equal to 0. There is no velocity change, there is no velocity gradient, therefore shear stress tau is equal to 0. Right? This is about different parts of the boundary layer. Now what is the laminar boundary layer, what is the turbulent boundary layer, what is the transition zone. That heads we are going to discuss now. That are, right, this is the boundary, this is the boundary, this is leading edge, right. What is laminar boundary layer, what is transition zone, what is turbulent boundary layer. So this is the, consider a free stream velocity flowing here, a thin smooth plate provided, a thin smooth plate provided, parallel to the direction of flow. Because of this thin plate provided in front of the flow, automatically the velocity at this point above the surface of the body or above the surface of the solid body is zero. Because of the viscous forces, because of the viscosity of the flowing liquid. Gradually from the boundary, the velocity gradually increases. That means the velocity gradient exists. Velocity gradient exists like this. Okay. So immediately this is the leading edge. This is the leading edge. Say point A, this is point B. From the leading edge or point A to point B, the boundary layer thickness is very thin. The boundary layer thickness is very thin. From point A to B, the boundary layer thickness is very thin. And also the flow in this zone is laminar, even though the main flow is turbulent flow. Main flow is turbulent flow, even though the distance from A to B, the flow is laminar, and this is flow within the small thickness. This zone is known as laminar boundary layer. Laminar boundary layer. Right? Now the distance from the leading edge to the point B, this is known as laminar zone. Laminar zone. Now laminar zone is determined, the distance of the laminar zone is determined by using the Reynolds number. This laminar zone depth x is determined by using the Reynolds number. Reynolds number equal to, we know formula, rho v d by nu. Rho is the mass density of the fluid, v is the velocity of flow, d is the diameter of the pipe in case of pipe flow, whereas in case of open channel flow, d is the hydraulic mean depth. Here this d is nothing but distance between the A and B. Therefore Re is equal to, Reynolds number is equal to rho v x. X is the distance from the leading edge to the end of the laminar boundary, divided by mu. Right? This x is determined by using a Reynolds number. In this case, Reynolds number is given by, Reynolds number is equal to 5 into 10 power 5. Then that zone is nothing but laminar zone. So here mass density of the fluid known to us, that is the 1000 kg per meter cube in case of standard liquid. V is the velocity of the flow here, and mu is the viscosity of the fluid. Only unknown x. Reynolds number is given, that is equal to 5 into 10 power 5. The Reynolds number value is equal to 5 into 10 power 5. That zone is known as laminar zone. So all are known to us. Reynolds number given here, mass density of the fluid we known, velocity of the fluid known, and viscosity is also known. Then x we are going to determine. Now this x, this is the laminar zone. Beyond the laminar zone or beyond the x, the boundary layer is disturbed and irregular, and also the thickness of the boundary layer is also gradually increases. The thickness of the boundary layer is also gradually increases, so that the flow changes from laminar to turbulent. This is laminar to turbulent. This zone is known as, the flow changes from laminar to turbulent. This zone is known as transition zone. transition zone. Right, this is transition zone, this is the laminar zone, this is the transition zone, this is the laminar boundary layer. Now beyond the transition zone, the boundary layer thickness continuously increases. The boundary layer thickness continuously increases, and also the flow in this zone is random, turbulent stage, so that the beyond the transition zone, the boundary layer thickness increases, the flow in this zone is also disturbed, very random. Therefore, this zone is known as a turbulent zone. That means the Reynolds number is more than 5 into 10 power 5, then calculated distance x, or the beyond the x is nothing but a turbulent zone. Right, one more zone is here, laminar sublayer, sublayer. This is the laminar sublayer. Right, this is laminar zone, this is turbulent zone, this is transition zone, this is laminar boundary layer, this is the turbulent boundary layer, this is transition zone. Right, laminar sublayer is the part of the turbulent boundary layer, because this is the turbulent boundary layer. Laminar subzone is the part of the turbulent boundary layer, but the velocity changes or velocity variations in this laminar sublayer is because of the viscous forces, viscous effects. Once again, the velocity variations in this laminar sublayer is because of the viscous effects. So that, strictly speaking, the velocity distribution in the boundary layer is parabolic. Right, now in case of laminar sublayer, the velocity variations is because of the viscous effects. Therefore, in this zone, the velocity gradient is linear. Strictly speaking, velocity gradient is parabolic, but this is linear because of the viscous forces. Now what is happening? Already I told you, if y is equal to 0, shear stress tau is equal to mu into du by dy. If y is equal to 0, velocity is equal to 0, automatically this is equal to 0, shear stress is equal to 0. And one more condition, if y increases from the boundary, velocity produces, automatically shear stress is equal to, we have some value. But in case of laminar sublayer, even though y is equal to 0, shear stress in the laminar sublayer is equal to mu into du by dy. This is the standard formula. Right, now the profile of the velocity variation in this laminar sublayer is linear. Therefore, du by dy equal to u by y. Therefore, tau, shear stress in the laminar sublayer, even y is equal to 0, very nearer to boundary. This zone is very nearer to boundary, almost all y is equal to 0. This is equal to mu into u by y. Right. In case of laminar sublayer, the shear stress exists. The shear stress is equal to mu into u by y, because the profile variation in this zone is linear. These are last class we discussed. Now we are going to discuss about boundary layer thickness. Boundary layer thickness. Boundary layer thickness. Right, what is boundary layer thickness? You know what is boundary layer. Boundary layer means the velocity at the boundary is 0, gradually increases at a certain distance. That velocity reaches to the free stream velocity. That thickness is nothing but boundary layer. Now boundary layer thickness means it is the distance measured. Boundary layer thickness means it is the distance measured from the boundary of the solid body in the y direction, where the velocity at one location is equal to 0.99 times the free stream velocity. That total thickness is known as boundary layer thickness. This boundary layer thickness is denoted by delta, right? Or the boundary layer, the velocity of the flow is reaches to free stream velocity is also boundary layer thickness. Now this boundary layer thicknesses are three types. One is displacement thickness, momentum thickness, energy thickness. Displacement thickness. Last class I have derived the formula regarding displacement thickness. Delta star is equal to integral 0 to delta 1 minus u divided by capital U into dy. This is derived in the last class. Now we are going to discuss about momentum thickness. Momentum thickness. What is momentum thickness? First definition. To compensate the reduction in the momentum of the flowing fluid on account of boundary layer formation, this boundary layer is shifted to a distance of theta. This shifting of this boundary layer to a distance theta, this is known as momentum thickness. What is the momentum thickness? What is the formula for the determination of the momentum thickness that we are going to write? Now first we are going to consider a free stream. The velocity at point B is 0. The velocity at point C is free stream velocity, that is u. The velocity at B is 0, the velocity at C equal to free stream velocity. That means here the velocity varies from 0 at the boundary and reaches the free stream velocity at C. This is known as, therefore the BC is known as boundary layer thickness, so that is denoted by delta, right? The distance BC is nothing but boundary layer thickness because the velocity varies from 0 to free stream velocity. Right, now again consider a section 1-1, that is x distance from the leading edge. This is the leading edge, this is the leading edge. Consider a section 1-1, that is x distance from the leading edge. Okay, now this is the velocity gradient or velocity profile. Consider a small section here, consider a small element here, that is depth of this element is dy, depth of this element is dy, and width of this element is b. This is the width is b, and that is y distance from the boundary, right? Consider a small element at section 1-1. The depth of the element is dy, width of the element is b, and that is y distance from the boundary, right? And the velocity over the strip is small u. Velocity over the strip is small u, at C is capital U, right? This is about different points taken into consideration by using this diagram. Right, now we are going to derive the expression. Right, here in this derivation you have 4 points. Point number 1, presence of boundary layer. This is the boundary layer. Presence of boundary layer. What is the mass of fluid? And absence of boundary layer, what is the mass of fluid? Once you know the mass of fluid, then here we are going to determine the momentum thickness. Presence of boundary layer, what is the momentum of the flowing liquid? Absence of the boundary layer, what is the momentum of the flowing liquid? These two heads we are going to determine. Once we are going to determine these two momentums, presence of boundary layer and absence of boundary layer, what is the difference between these two? Because if there is no boundary layer, there is no any boundary, the free stream velocity will continue over the small strip with a velocity capital U. Because of the boundary layer here, there is no free stream velocity over the strip, only having the small u. So that the momentum of the flowing fluid with boundary layer is less than the momentum of flowing fluid without or absence of the boundary layer. Therefore, the difference between these two, we are having the loss of momentum flowing through the boundary layer. That is the 2 points. Once momentum of the flowing fluid determined over the strip, then we are going to determine the momentum of flowing fluid or loss of momentum of flowing fluid over the entire thickness BC, or entire thickness BC, that is nothing but delta. Right, that is the first point. Next one, so to compensate for the reduction in the momentum of the flowing fluid on account of boundary layer formation, this boundary layer is shifted to a distance theta. This boundary layer is shifted to a distance theta, so that there is a reduction, compensation of the momentum of flowing fluid over this boundary. There is a reduction that we are going to determine, right? Equating the momentum of flowing fluid because of the presence and absence of the boundary layer difference, and the shifting of the boundary layer to a distance theta. Equating these two, we get the equation for the momentum thickness. First one, presence of boundary layer. Presence of the boundary layer, what is the momentum of the flowing fluid? Right, momentum of the flowing fluid, presence of the boundary layer equal to momentum equal to mass into velocity. Right, what is mass? First we are going to determine. Mass is equal to what is the standard formula? Mass density into area into velocity. Area into velocity, right? Mass density very clear. What is the area? Here we have taken one small strip, that is the depth is equal to dy, width is equal to b, area is equal to b into dy is the area. Then velocity, what is the velocity? Velocity over the strip is small u. Velocity over the strip is small u. Therefore, mass equal to rho into area b into dy into velocity is small u. This is the mass. Right. Now, momentum, presence of the boundary layer equal to mass rho into b into dy into u is the velocity into velocity u. Right. Then this is the presence of the boundary layer, absence of the boundary layer. Absence of the boundary layer, what is the momentum of the flowing liquid? What is the momentum of the flowing fluid? Right, if this is the obstruction provided here, one plate or one boundary, if there is no obstruction, absence of the boundary layer, the velocity of flow is equal to free stream velocity over this strip. If there is no boundary here, automatically the velocity of the fluid over this strip is free stream velocity. That is only the difference. Now momentum, absence of boundary layer, momentum of the flowing liquid, absence of the boundary layer equal to same formula, mass into velocity. Mass already we have determined here. Velocity is absence of the boundary layer. The velocity over the strip is capital U, or free stream velocity. Right. This is equal to, mass is equal to, what is the formula? Rho into b into dy into small u into capital U. Capital U is the velocity, absence of the boundary layer. Right. This momentum of the flowing fluid, presence of the boundary layer, momentum of the flowing fluid, absence of the boundary layer. These are the momentums of the flowing fluids only over the strip. Now we are going to take into consideration entire boundary layer. The boundary layer, this is nothing but delta. What is the total? Now total. Now before that, first we are going to determine what is the loss of momentum because of the boundary layer formation. Loss of momentum is equal to the momentum of the flowing fluid, absence of the boundary layer, that is rho b dy small u into capital U minus momentum of the flowing fluid, presence of the boundary layer, that is rho b dy u into u, small u. Right. Now this is equal to rho b small u capital U minus small u into dy. Now this is the loss of momentum because of the boundary layer. Loss of momentum because of the boundary layer over the strip is equal to rho b u bracket begin capital U minus small u into dy. Rho is the mass density of the flowing liquid, b is the width of the strip, u is the velocity of the strip, velocity over the strip, capital U is the velocity, free stream velocity. Now total loss of momentum, over the boundary layer delta, that is equal to integral 0 to delta. Why? Because here at a distance y, delta is equal to 0, at a distance y is equal to 0, delta is equal to 0, y is equal to y, delta is equal to delta. Therefore the velocity varies from 0 to y within the distance of delta. Therefore 0 to delta rho b u capital U minus small u dy. This is the one equation. Right. Next, so now because of the reduction of the momentum, this boundary layer is shifted to a distance of theta. At theta distance, the velocity of the flowing liquid is capital U. Okay. Therefore here we are also, what is the reduction of the momentum because of this boundary layer is shifted to a distance theta, right? Therefore momentum at a distance theta equal to same formula, mass into velocity, right? What is mass? Mass is equal to same formula, mass density into area into velocity, right? Mass density of the fluid is common. There is a fluid, standard liquid 1000 kg per meter cube, any other liquid, that density into specific gravity of that liquid, mass density is common. Next, area. What is the area? That is, we are going to determine the momentum at a distance theta. That is theta into b is the width. Earlier case we have taken area is equal to b into dy. Width is equal to b, depth is equal to dy. Now in place of this dy, we are going to take theta, because that boundary layer is shifted to a distance of theta. This is the area into velocity over this theta is capital U, right? Now momentum of the flowing fluid at theta equal to mass, that is equal to rho into theta into b into capital U. This is the mass into velocity is u. Now this is the loss of momentum because of the boundary layer is shifted to a distance theta. This is equation number 2. Earlier already we have determined presence of the boundary layer, absence of the boundary layer, the momentum of the flowing liquid, the difference or loss of momentum also determined earlier. That is equation number 1. Therefore the equating these two losses, finally we are going to get the what is the theta, what is the momentum thickness theta, right? So this is equal to rho into theta into b into u is equal to loss because of the presence of the boundary layer, absence of the boundary layer, that is equal to p b integral u that is equal to capital U minus small u dy, right? Now rho cancel, b cancel, therefore theta is equal to, this is 0 to delta, theta is equal to integral 0 to delta small u by, this is capital U square taken that side, into capital U minus small u dy. Now this is equal to integral 0 to delta small u divided by capital U, capital U divided by small u, this is 1 u inside, minus small u divided by capital U into dy. Cancel, therefore theta momentum thickness equal to integral 0 to delta small u divided by capital U 1 minus small u divided by capital U dy. This is the formula for the determination of the momentum thickness, right? Right. Now we are going to discuss about energy thickness. First, what is the definition of the energy thickness? Energy thickness is the distance. Energy thickness is defined as the distance measured perpendicular to the boundary, because the boundary layer is shifted to a distance delta double star. This energy thickness is denoted by delta double star. So once that boundary layer is shifted to a distance delta double star, there is a reduction in the kinetic energy of the flowing liquid. That distance from the boundary is known as the energy thickness. Right. Now, what is the formula? What is the derivation? What is the equation for the energy thickness that we are going to derive here? Now, here, consider a free stream velocity u. Flowing over the thin, smooth plate. That plate is put it in the parallel direction, in the direction of the free stream velocity. Right? And again, consider a section 1-1. Consider a section 1-1 at a distance x from the leading edge. Consider that section is considered x. 1-1 section is considered at a distance x from the leading edge. Now we are going to take one small strip. The depth of the small strip is equal to dy. That is y distance from the boundary, and the velocity over the strip is small u, and the width of the strip is b. Right? 4 points. One, the velocity over the strip is small u, the depth of the strip is equal to dy, that is y distance from the boundary, and width of the strip is equal to b. Right? Right, here also the velocity varies. At velocity at point B is equal to 0, the velocity at point C is equal to u, that is free stream velocity. Therefore, the velocity varies from 0 to free stream velocity, that is from B to C. Therefore, this B to C, this depth is known as theta, that is known as boundary layer thickness. Theta is nothing but delta is nothing but boundary layer thickness. Right. Right. Now we are going to derive the equation for the energy thickness. Right. In here also same 4 points we are going to follow. First, the energy thickness. For the determination of equation for the energy thickness, first we are going to determine the kinetic energy presence of the boundary layer. Second point, kinetic energy absence of the boundary layer. And third point, what is the difference between the kinetic energy because of the provision of the boundary layer, absence of the boundary layer? That difference we are going to determine. That determined loss of kinetic energy that is over the strip, that is taken with a integral of 0 to delta, then we have the entire boundary layer thickness delta. Right, first presence of the boundary layer. Presence of the boundary layer. Presence of the boundary layer, energy thickness. Energy thickness or kinetic energy thickness equal to presence of the boundary layer. Kinetic energy is equal to half mass into velocity square. Half mass into velocity square. Right, what is mass? Mass equal to mass density into area into velocity. What is mass density is denoted by rho. Mass density is denoted by rho into area. Area is equal to depth of this strip is equal to dy, width of the strip is equal to b. Therefore, this is the area. B into dy is the area. Into what is the velocity? Velocity over the strip. Because this is the presence of the boundary layer, velocity over the strip is equal to small u. Right? Now, this is equal to half mass rho b dy into u into velocity square, that is velocity square. Right? This is presence of the boundary layer, kinetic energy equal to, this is the formula. Right? Absence of the boundary layer. Absence of the boundary layer, if there is no boundary here, the free stream velocity is moving with the same velocity over this strip. That means absence of the boundary layer, the velocity of flow over the strip is taken as capital U. That is the difference. Right? So, here absence of the boundary layer, kinetic energy or simply energy, absence of the boundary layer is equal to same formula, half mass into velocity square. Mass already we determined, that is equal to, right, this is equal to half, mass is nothing but rho into b into dy, right, into u, this is the mass, into capital U square is the velocity over the strip, absence of the boundary layer. Right? Now loss of kinetic energy because of the formation of the boundary layer. Loss of kinetic energy because of the formation of the boundary layer equal to, that is absence of the boundary layer kinetic energy minus presence of the boundary layer kinetic energy. Absence of the boundary layer kinetic energy is equal to 1 by 2 rho b dy into u square minus presence of the boundary layer half rho b into dy into u square. Right? Right, this is equal to 1 by 2 rho b small u taken out, capital U square minus small u square dy, half rho b u, right, dy capital U square minus small u square, capital U square minus small u square. This is the loss of kinetic energy, formation of the boundary layer over the strip. Now the loss of kinetic energy, entire boundary layer thickness, that is B to C. Right. total loss of kinetic energy for the entire boundary layer thickness delta is equal to, that is B to C is equal to integral 0 to delta 1 by 2 rho B U into capital U square minus small u square dy. Loss of total kinetic energy for the formation of the boundary layer. Now this boundary layer is displaced, to a distance delta double star. Because of this displacement of the boundary layer, there is a reduction in the kinetic energy or loss of kinetic energy. Therefore, reduction in the kinetic energy or loss of kinetic energy because of the displacement of the boundary layer to a distance delta double star. The velocity at this delta double star is free stream velocity capital U, right? That is only difference. Now kinetic energy is equal to half mass velocity square. Mass equal to rho into area into velocity, right? Rho is nothing but same. Area here delta double star is the thickness into B is the width into velocity of the flow is capital U, right? Therefore half rho delta star star into B into capital U into velocity square capital U square. This is the loss of kinetic energy because of the boundary layer is shifted from the original stage to at a distance delta double star. The velocity at that point is equal to capital U. So this is one loss. Already we have determined total loss of kinetic energy because of the formation of the boundary layer, that is in the earlier equation. The equating these two equations, now we are going to get the thickness of the boundary layer, that is equal to half rho delta star star width of the plate into U cube is equal to half rho B small u into capital U square minus small u square dy, right? This is we have in the earlier equation, right? Constant rho constant, b is also constant. Therefore delta star star, that is the energy thickness into capital U cube is equal to integral 0 to delta small u capital U square minus small u square dy, right? Therefore delta star star or energy thickness is equal to 0 to delta small u divided by capital U cube, that is capital U square minus small u square dy, right? This is equal to integral 0 to delta small u divided by capital U, that one, this is cube. Therefore capital U square minus capital U square small u square divided by capital U square dy. Now this gets cancelled. Energy thickness is equal to 0 to delta small u divided by capital U, bracket begin, this cancel, 1 minus small u square by capital U square dy. This is the formula used for the determination of the thickness of the energy or energy thickness. Integral 0 to delta small u by capital U